Chapter 8 is about wind and weather. Our driving question is what forces control the speed and direction of the wind. There are several forces that govern the wind. We'll talk about each individually, but the overview is we have first and foremost the air pressure gradient force, and then the centripetal force, which is actually a consequence of several other forces, but for our discussion we'll just call it centripetal force. The Coriolis effect, which isn't really a force so much as it is an effect, but it does have an impact on wind, friction, and gravity. Let's start by looking at the air pressure gradient, which exists whenever air pressure varies between locations. So remember that nature doesn't like to have things organized. So when we have high pressure in one area and low pressure in another area, nature tries to equalize that, and it does so through winds. So winds want to blow from areas of high pressure to areas of low pressure. We can talk about a horizontal pressure gradient, which moves horizontally across the surface of the Earth. And we can also talk about a vertical air pressure gradient, which is a little bit different. Remember that air pressure decreases with altitude in the atmosphere. And so in that sense, we have high pressure at the surface and lower pressure aloft, and therefore an air pressure gradient as we move up in the atmosphere. But for most of our discussion, we are concerned with the horizontal pressure gradient. So the air pressure gradient is measured in the direction of greatest change, and what we end up with is wind flow perpendicular to isobars. So if it were just a matter of the air pressure gradient, wind would flow across the isobars perpendicularly to go from areas of high pressure to areas of low pressure. And you see from this graphic where the isobars are tightly packed, like they are in this area, you're going to have a stronger gradient and therefore stronger winds blowing than you would for areas where the isobars are widely spaced, and therefore we have a weak gradient and weaker wind flow. Remember, when we look at isobars on a map, we draw them at a standard interval of 4 millibars, and we do that so we can see these kinds of trends in the isobars and therefore the winds. We can see where they're steeply packed or where they're shallowly packed and get a sense of the gradient and the corresponding wind flow. So here's the same concept. When we have closely spaced isobars, we're going to have tighter or a stronger pressure gradient and therefore stronger winds. So pressure in this case is decreasing as we move northward, so the wind wants to blow from high to low pressure, and it will do so much quicker here because of the steeper pressure gradient, as opposed to the wider spaced isobars like we see here. Again, high pressure at the bottom and lower pressure at the top, so the winds still want to blow in the same direction but will do so slower than with the top example. The second force that governs the wind is centripetal force. Centripetal force is the center-seeking force that you feel when you're going upside down on a roller coaster, for example, or if you do something like this picture shows. I don't think I've ever tied a rock to a string and twirled it around, but I've certainly twirled other things around. And you know that the rock in this example, as soon as you start spinning it, it wants to just take off and go straight away. But because it's confined to the string, it has to go in the direction that's specified here. And the force that's keeping it on a curved path is the centripetal force. So Newton's first law of motion says that an object moving in a straight line wants to continue doing so unless there's some force acting on it. So as soon as you start to twirl this string, that rock wants to go in a straight line, but there's the centripetal force acting on it that keeps it in a circular path. So this force is directed perpendicular to the direction of the object's motion towards the center of the circular orbit. So if the rock wants to go in a straight motion, the centripetal force is acting exactly perpendicularly to it and directed towards the center of the orbit. So again, this is not a single force. We're calling it a single force in this discussion, but it's actually a little more sophisticated than that. There are other forces operating on atmospheric winds, and this one we're just going to call the centripetal force. So it's relevant for winds that are blowing on a curved path. Next is the Coriolis effect. Again, not a true force, an effect, and it's an effect that has to do with the fact that our Earth is rotating on its axis. So if we were to view the Earth from distance, from space, we would see the Earth rotating from the west to the east as we're looking at it in the northern hemisphere. And we would see a straight line of motion. So if we had something like a weather system that was making its way across the United States and we were up on the space shuttle looking down at the Earth, we would see the motion of that storm moving basically horizontally in the simplified version. In reality, down here on the Earth, we are rotating. And because of that rotation, it causes the motion of free moving things like a storm system in the atmosphere to apparently change its direction or be deflected to the right in the northern hemisphere. So something that looks like it's moving straight across, like in this first picture, in reality, because the Earth is rotating, its direction gets deflected to the right relative to that wind flow. So if the system is moving this way, it gets deflected off to its right. And this is called the Coriolis effect. It's exactly the opposite in the southern hemisphere. So instead of a deflection towards the right, we would have a deflection towards the left. So here's a graph that shows the different deflections that you might see and the wind direction based on the wind direction. So up here in the northern hemisphere, if we have, say, a wind that's blowing directly northward, that's the dashed line here, the Coriolis effect wants to deflect it to the right. All right, so all of these are the same thing. If the wind direction wants to move, in this case, directly due east, the Coriolis effect deflects it to the right, so its actual direction would change accordingly. So you can see all of these different situations. The Coriolis effect is strongest up at the poles. That's where its maximum deflection is going to exist. And it's weakest at the equator. And then when we come into the southern hemisphere, the deflection is to the left. So if the wind wants to blow poleward to the south here in the southern hemisphere, the Coriolis effect deflects it to the left relative to the wind direction. And similar for all these different situations. So the faster moving objects are going to be deflected more than slower ones. And the longer the trajectory, the greater the shift of the Coriolis effect. Next force is friction, and friction has to do with the resistance that an object meets as it comes into contact or moves in contact with another object or medium. Friction, when we talk about the winds, is only relevant to the lower portions of the atmosphere where the Earth's surface presents a frictional layer. And we call the layer of the atmosphere where friction comes into play the atmospheric boundary layer. So boundary layer meteorology is meteorology that's close to the Earth's surface where friction comes into play. And when we look at going high in the atmosphere, as we get up to about 1,000 meters, which is about 3,300 feet, friction becomes less of an issue. So it's really just in the boundary layer, the first 1,000 meters of the Earth's surface or atmosphere, where friction comes into play. And we get turbulent winds. So if we look at how fluid flows, which you can read about in the textbook, it's characterized by eddy motions, and we get these little turbulent eddies as gusts of wind down in the boundary layer. So the main point here is that friction is going to slow down winds closer to the Earth's surface. Another force affecting winds is gravity, and gravity, of course, is the force that holds objects to the Earth's surface. So remember that we have general decrease of air pressure as we move upwards in the atmosphere. And I mentioned earlier there's a vertical pressure gradient with higher pressure at the Earth's surface and lower pressure higher up. So the tendency is for the Earth's atmosphere to just all the winds to move up, right, to blow straight up. But that doesn't happen because gravity at the same time is pulling everything closer to the Earth's surface. So if we look at these two forces in combo, we get something called hydrostatic equilibrium, which is the balance between the force of gravity pulling an air parcel down towards the surface of the Earth versus the vertical pressure gradient force, which wants to pull that air parcel higher up in the atmosphere. So these two things are balanced. These two forces are balanced so that in general we have the air parcel staying right where it is. Now let's talk about how we can combine some of these forces to affect wind motion, and we'll start with something called the geostrophic wind. And the geostrophic wind refers to the horizontal movement of air, so no curvature here, and we are above the atmospheric boundary layer, so away from the Earth's surface where friction would come into play. At this height in the Earth's atmosphere, the only two forces that are at play in a geostrophic wind are the pressure gradient force and the Coriolis effect. So in this example here, we have a starting point. You can imagine a parcel of air and what it wants to do. We're higher up in the Earth's atmosphere, so you see lower pressure readings here for these isobars than you would see at the surface. But still, you see we have high pressure lower in the map and lower pressure higher up here. So the pressure gradient force wants to have winds blow from high pressure to low pressure right across those isobars, perpendicularly. So that's what happens. This air parcel wants to start moving off in that direction. But as soon as it does, the Earth is rotating underneath it, and so we have the Coriolis effect kick in, which pulls the direction of that air parcel to the right in the northern hemisphere. So these lines represent the force and the direction of the wind. So the pressure gradient force is the straight perpendicular to the isobars force that you see here. And then counteracting that, we see the Coriolis effect. So the direction of that air parcel ends up being deflected in the way you see in this red line. So again, from its new direction, it wants to move according to the pressure gradient force directly to the low pressure. But again, the Coriolis effect deflects it to the right. And you can see that this play continues until the Coriolis effect becomes more and more apparent. Remember, the longer the trajectory, the stronger the Coriolis effect is going to be, until we have the balance between the pressure gradient force and its tendency to move that air parcel directly to the low pressure versus the Coriolis effect, which is pulling the movement of that air parcel to the right. It's deflecting it to the right. When the pressure gradient force and the Coriolis effect come into equilibrium, that wind is going to be blowing parallel to the isobars. And that's what we call the geostrophic wind. It's a wind that's following a straight path parallel to the isobars, and it's a result of the balance between the pressure gradient force and the Coriolis effect. There is no friction, and here we're looking at straight movement, so there is no centripetal force. There's a little rule of thumb here. Oops, lost my place. There we go. There's a little rule of thumb here that says if you're standing in the northern hemisphere and the wind is blowing to your back, so you imagine you're standing here with the wind blowing to your back. Of course, you'd be really tall because this is high up in the atmosphere. You're going to have low pressure on your left and high pressure on your right. The next type of wind we'll talk about is the gradient wind, and it's similar to the geostrophic wind in the sense that it's up out of the boundary layer, so no friction is coming into play here. It is different than the geostrophic wind in that this time we're looking at a curved path. Geostrophic is just for straight wind flow. Gradient wind is for a curved path. So we have another force that kicks in, and that is the centripetal force that wants to pull the wind or the air parcel's movement inward. So here we're higher up in the Earth's atmosphere. We're going to start with this low pressure cell. You see a lower pressure reading here compared to the next isobar, so the pressure's increasing as we move away from the center of low pressure. So because this is a low pressure, the pressure gradient force dictates that an air parcel wants to rush right into that low pressure cell. And in fact, we see in this orange line the force of the pressure gradient force. It wants to pull that air right into the center of that low pressure cell. But as we saw, as soon as it starts to move, the Coriolis effect deflects that wind flow to the right. So we end up with a flow that's going to be parallel to the isobars. But this time, because we have a cell of low pressure, we also have the Coriolis effect, the centripetal force, which is the CE, the green line here, that's pulling that wind or that air parcel inward. So we have a balance of three different forces. On one hand, the pressure gradient force and the centripetal force, which are pulling things inward towards that low pressure cell, and they're balanced by the Coriolis effect, which is pulling the winds outward. So our net effect around the low pressure cell is that we have winds blowing in a counterclockwise motion, and this gradient wind it's going to blow parallel to the isobars and counterclockwise. This is in the northern hemisphere. If we were in the southern hemisphere, the same forces would be at play, but because the Coriolis effect pulls things or deflects things to the left in the southern hemisphere, we would have rotation around the low pressure cell be clockwise. When we look at a high pressure cell in the northern hemisphere, this time the pressure gradient force wants to pull the wind flow or that air parcel out of that high pressure cell so that it would be perpendicular flow away from high pressure. But as soon as the wind moves in that direction, the Coriolis effect kicks in and deflects the motion of the air parcel, the wind flow, to the right in the northern hemisphere. And in addition here, we have the centripetal force, again, which is that inward acting force that wants to make curved flow. So the net effect here in the northern hemisphere is that we're going to have, again, a gradient wind higher up in the atmosphere, no friction, that's parallel to the isobars and now is moving clockwise around this high pressure cell. The opposite would be true in the southern hemisphere. We'd have parallel flow, but it would be moving in a counterclockwise motion for a high pressure system. So this is the gradient wind. Again, no friction. We're up higher up in the atmosphere. Now let's talk about what's happening at the surface, and essentially it's all the same forces at play plus another one, which is friction. And the effect of friction, remember, is to slow the wind down. So friction is going to combine with the Coriolis effect to balance the horizontal pressure gradient force. So here we're looking at non-curved flow. So we're looking at just the movement without centripetal forces. So we have high pressure and low pressure. You can see by the millibar readings that we're at the Earth's surface. So the pressure gradient force takes this parcel and it wants to move it from areas of high pressure to low pressure, so it wants to have the winds take off in this direction. You see from the pressure gradient force line here. As soon as it moves, as soon as the air starts to move, the Coriolis effect kicks in and deflects the motion to the right by exerting its effect and causing the winds to change direction. And in addition to that, we have friction. So here's the magnitude showing friction, which always works exactly opposite the wind flow. So we have a net effect here between the Coriolis effect and the force of friction, which is called R. So it's just the combination of the Coriolis effect and the force of friction, and it's acting in direct opposite of the pressure gradient force. And so when we combine these two forces, the actual wind flow is going to blow not parallel to the isobars like it did higher up in the atmosphere with the geostrophic wind, but this time it's going to flow across the isobars in such a way that it's going to be generally moving out of the high pressure system. So you can see that its net effect is away from the high pressure and towards the low pressure, though it's not as direct as the pressure gradient force would have it. So we end up with cross isobaric wind flow, and that angle at which the wind flow is going to cross the isobar varies between 10 to 45 degrees, just depending on atmospheric conditions. So here's an example of surface winds as they would blow with respect to a cell of high pressure and a cell of low pressure. So remember, with high pressure, higher up in the atmosphere, as we just saw, the wind flow in the northern hemisphere is clockwise. So clockwise around a high pressure cell. We call that an anticyclone. So with a high pressure, we have highest pressure values towards the center of the cell, and they decrease as we move out. The pressure gradient force wants that wind to just blow straight across the isobars perpendicularly, but as soon as the wind moves, it's subject to the Coriolis effect, which deflects things to the right in the northern hemisphere, and so we get this rightward deflected motion. And we have the force of friction now, which slows things down. So instead of having that gradient wind like we saw in the higher atmosphere, we now have this net effect of winds flowing clockwise and out of the high excuse me, clockwise and out of the high pressure cell in the northern hemisphere. Again, it would be just the opposite in the southern hemisphere. Around a high pressure system in the southern hemisphere, it would still be an anticyclone, but the winds would be moving counterclockwise and out. In the northern hemisphere, for a low pressure cell, at the surface, this time we have our lowest pressure here and increasing pressure as we move out. The pressure gradient force wants the winds to blow directly to the heart of that low pressure cell, perpendicular to the isobars. As soon as the wind moves in that direction, it's deflected to the right. And then friction further slows down the wind and causes this motion of winds that are blowing in a counterclockwise way and into the low pressure cell. So this is called cyclonic flow. And this is how it happens in the northern hemisphere. Of course, in the southern hemisphere, we would have clockwise motion into the low pressure cell. So just to reiterate, our forces change with altitude. So the closer we are to the Earth's surface, the more impact friction is going to have. So here we are, you see the blue isobars and high pressure and low pressure close to the Earth's surface. And we have the pressure gradient force wanting to pull that air perpendicular to the isobars right into the low pressure. But as soon as it does, we have the Coriolis effect and friction, because we're close to the Earth's surface, come into play. And so the actual direction of the wind flow is given by this little line here. So we're still moving towards the low, but we're crossing the isobars at an angle. As we go higher up in the atmosphere, you can see the power of friction is decreasing. We still have it, but it's less of an effect. And so we're going to be crossing the isobar at a smaller angle. We're moving more towards geostrophic flow, which once we get up past the boundary layer and away from the Earth's friction, we have that geostrophic flow, that parallel to the isobars flow that's a combination of the pressure gradient force matched by the Coriolis effect. So if we combine everything together and look at a weather map here, here we see we have a low pressure cell, another low pressure area here, and then high pressure areas. And you can see the isobars. You get a sense of where the winds are going to be blowing the strongest by where the isobars are tightly packed, and where the winds are going to be very light, where the isobars are stretched farther apart. We have areas of curvature. We have ridges around high pressure cells. So here's a high pressure cell. We have a bit of a ridge that's developed here. Here's a high pressure cell. We have a bit of a ridge that's developed here. And then we have troughs around our low pressure cells. So this would be a trough around a low pressure cell. And then here's another trough around this low pressure cell. This is illustrated a little bit nicer in this image, which is an upper atmosphere image. You can see by these ISO lines, it's a little bit different here. These are not pressure values this time. Instead, what happens with the upper atmosphere is we look at a particular pressure level. So in this case, 500 millibars. And we look then at the heights, the altitudes at which 500 millibars occurs. So in effect, it's showing us the same thing. It's showing us a sense of the pressure gradients higher up in the atmosphere. It just does it a little bit differently. And you can see stronger winds higher up in the atmosphere because there's no pressure, or sorry, there's no friction. And we can see very clearly these ridges of high pressure and these troughs of low pressure, and the very tightly packed isobars indicating very strong wind movements, in this case the jet stream higher up in the Earth's atmosphere, which we'll talk about a little bit later in this semester. And then here's a ridge of high pressure that's been identified. The continuity of wind refers to looking at the flow of winds not just around a high pressure cell or a low pressure cell, but vertically as well. I touched on this a few chapters ago, and we'll talk about it again here. So in this case, we have a high pressure cell down at the Earth's surface, and we know that the net movement of air is out of the high pressure. It may not go across the isobars like the pressure gradient force would want, but the net effect is for winds to move out of that high pressure. This is called divergence, when you have winds blowing away from each other like you see here. And then it could create a vacuum here, but what happens is air from higher up in the atmosphere sinks down to fill that gap. So with a surface high pressure cell, if we were to look at the circulation in the vertical air above that high pressure cell, we would have sinking air. Sinking air is not conducive to cloud formation, so we typically have fair weather with high pressure cells. And then higher up in the Earth's atmosphere, we would have convergence. Convergence can happen with winds blowing directly towards each other. And convergence can also happen, as we see here, where wind slows down. So it's moving very quickly and then it slows down. And so there's a convergence here. There's a piling up of air, if you want to think of it that way. And because there's a piling up of air, there's air available to sink down and then diverge down at the Earth's surface. So we have this kind of circulation that takes place over a surface high. Just the opposite is happening over a surface low. Now we have surface convergence, air coming together, and once it piles up, it meets and it piles up, it has nowhere to go but up. So we have rising air, and then it meets air higher up in the atmosphere where it's diverging. And again, it could be diverging directly, where these arrows would be pointing away from each other, or in this case, it's diverging because different speeds of the wind. The wind speed is moving slower and then faster, and it leaves a space for this air to exist higher up in the atmosphere. So we get a different type of circulation, and this rising air, remember, contributes to the instability of the atmosphere. We have rising air that makes the atmosphere unstable and conducive to cloud development and storm development. This is why cyclones, or low pressure cells at the surface, are associated with stormy weather systems with clouds and precipitation. We can also talk about the continuity of wind with respect to different surfaces that the wind is going to encounter. So here we have a rough land surface and then a smoother water surface. So in general, water is much smoother. It presents less friction than the land does. And so if the primary wind flow is in the direction that you see here from the left of the picture to the right, we have a lot of friction encountered by the wind. And then as soon as it meets this smoother surface, we have the wind speeding up. So it's moving slower because of friction, and then it speeds up once it comes over the lake surface, and we end up with divergence. Right, so it's moving faster. It kind of leaves a space for air to sink down closer to the surface. And remember, sinking air is stable air, so we do not have the potential for cloud development. So we'll have clearer skies over on this side of the lake than we do over on the other side, which is the opposite story. Now the winds are blowing off of this smooth lake surface, so low friction. Suddenly the winds meet the land surface, which has more friction, and the winds slow down. So they kind of pile up in this area. And when they do, there's nowhere for them to go but up. We have convergence and ascending air, and with ascending air, the development of clouds and possibly precipitation. So this is one way that lake effect snow, or just lake effect weather for that sense, takes place because of the difference in friction between the land and the water and the resulting divergence and convergence. We measure wind speed and wind direction with different instruments. First, for wind direction, remember that wind direction is always given by the direction the wind is coming from, not the direction it's blowing to. So for example, a northwesterly wind is a wind blowing from the northwest and to, in this case, the southeast, but we call it a northwesterly wind. The most common instrument to measure wind direction is called a wind vane, and here's a picture of kind of a recreational wind vane. And the vane is counterweighted so that the arrow points into the wind. So when you see a wind vane, however sophisticated, it is pointing into the wind. So this one has a kind of a compass associated with it, so you can see it looks like we have a southerly wind in this case. A more simple device is a windsock, which you see around airports a lot of times, and windsocks simply blow downwind. So they don't point into the wind like our wind vanes do, but they blow with the wind. So you can look at it very quickly and see, oh, the winds are blowing in such and such direction. Wind speeds can be estimated by the Beaufort scale, and you can read about this in the textbook. The Beaufort scale is basically just a way of looking at what's happening around you. What's blowing? Are leaves on the trees blowing? If so, then there's an associated wind speed. Is the whole branch on the tree blowing? Okay, then the wind speed's going to be in a different category. And so on. So there's different ways that you can look at what's happening to the things on the Earth's surface as they interact with the wind to get a sense of wind speed. Wind speed is measured by various instruments. A cup anemometer is the picture you see up here, which has these little cups that just blow. This thing just spins based on the wind speed. And then there's a sensor in there that measures how quickly it's rotating, and it sends that to a computer as a measure of the wind speed. Aerovanes are guys that look like this. You may have seen these. They have blades and a propeller up here and then a fin on the back. And so the propeller is measuring wind speed, and then the fin is able to turn into the wind. So it also indicates wind direction. So we get both things, wind speed and wind direction, with one of these guys, one of these aerovanes. Now more commonly used by the American Meteorological Society and the National Weather Service for the official stations that monitor weather conditions at the surface is a sonic anemometer, and it consists of 3 arms like you see here that send and receive ultrasonic pulses. So there's a sound wave that travels just right between these things, and the way that the winds interact with that sound wave tell us about the wind speed and wind direction. So it's maybe not as interesting to look at if you come across a weather station and you're trying to identify what the different instruments are. This one isn't moving in any way, but it is giving an accurate measurement of wind speed and wind direction. So when you monitor any type of meteorological phenomena, in this case winds, it's important that your instruments be placed in the proper position. There are specifications for how the instruments should be mounted. And for winds, we have a requirement that they should be mounted 10 meters or 33 feet above the ground. So we don't want it too close to the ground because there's a different thing happening with wind close to the ground. We don't want it too high up in the atmosphere unless we are trying to measure higher atmosphere winds. So 10 meters is the standard. And you want to try to avoid like rooftop locations and stuff like that, because even though you're higher above the ground, you're still presenting a surface. The roof is still a surface that's going to interact with the winds. And then to get wind measurements higher up in the atmosphere, we use radiosondes, which are the weather balloons that have instrument packs connected to them. And if we chart the path of the radiosonde through GPS, we get a sense of how fast it's moving and in what direction, and therefore we can get the wind speed and wind direction. We can look at satellite imagery for the same location over a period of time, maybe every hour, every few hours, and we can get a sense of how fast a storm system or something is moving. If we can identify it in the satellite image, then we can compare its location at different times and therefore measure its speed. And then we have these new devices called wind profilers, which you can read more about in the textbook. And they measure winds higher up in the atmosphere using microwaves that are sent out higher up into the atmosphere and then able to be traced to give us an indication of how fast winds are moving higher up. Finally, there are different scales of weather systems. When we talk about meteorology, we usually break it down into the scale. And here we see the 4 basic scales, starting with microscale systems. Here we're just looking at winds, but you can really break this down into any phenomenon. But for microscale, you can see that the space involved is 1 meter to 10 kilometers. So really close to the Earth's surface, very small scale. And the time scale is going to be accordingly micro. So we're talking about things that exist in seconds up to maybe an hour. And an example here would be a very weak tornado. So out west we're more familiar with dust devils and things like that. So a very weak kind of tornado or a strong dust devil would be an example of a microscale system. Next we have the mesoscale. And this deals with weather that affects maybe a large city or a county. So something like a thunderstorm, or if you're by the beach, a sea breeze. So the scale here, the geographic scale is 10 to 1,000 kilometers. The time scale is hours to a day. And you can think of like a severe thunderstorm. So like our monsoons that come in. The synoptic scale goes up a level. So these are continental or oceanic in nature. So things like migrating cyclones, hurricanes, and air masses, which we haven't talked yet about in this class, but we will soon. So the geographic scale is on thousands of kilometers, so 1,000 to 3,000 kilometers. These are systems that persist for days up to a week. And an example they give here is an Arctic high, which is a high pressure system up in the Arctic. And then the largest scale is the whole planet, a planetary scale system. These would be large-scale wind belts that encircle the planet, like westerlies or trade winds. They encompass thousands of kilometers of distance, and they last for weeks up to a month. And we'll talk about these various circulation patterns in the next chapter.